Now for example 1, suppose that populations of rabbits and wolves are described by the Lotka-Volterra equations with the constant k is equal to 0.08, the constant a, which is 0.001, constant r is 0.02, and the constant b is 0.00002. The time t is measured in months. So for part A, we want to find the constant solutions called the equilibrium solutions and interpret the answer. So recall what equilibrium solutions mean, as that means when it equals 0. Now, in step number 1, we're going to use the Lotka-Volterra equations that were given at the beginning of this section. So we have dr over dt, which is equal to the constant k, which is 0.08 r, minus the constant a, which is 0.001 r times w. And then dw divided by dt is equal to the constant r, which is 0.02 times a negative w, plus the constant b, which is 0.00002 rw. And so another way of writing this is that r prime is equal to r times 0.08 minus 0.001 w, since we factored out the r. And on this side, we'd have w prime, which is equal to, factoring out the w, negative 0.02 plus 0.00002 r. Now, if we're talking about the equilibrium solutions, that's when r prime is equal to r, and that means that when it would be equal to 0. So one solution is given by when r is equal to 0 and w equals 0. And this makes sense because if there are no rabbits or wolves, the populations are certainly not going to increase. So the other constant solution is the following. So we're going to take r times 0.08 minus 0.001 w, which is what we have here, and we're going to set that equal to 0 since that is an equilibrium point. If we divide both sides by r, 0 divided by r is now r, and now we can solve for w by subtracting both sides by 0.08 and dividing by negative 0.001, so w is going to equal 80. For the other equation, again, we can set this equation equal to 0, so where the derivative is equal to 0, that's where you have your equilibrium. So we can divide both sides by w and then solve for r by adding 0.02 to both sides and dividing by 0.00002, and therefore r is going to equal 1,000. So the equilibrium populations consist of 80 wolves and 1,000 rabbits. And this means that 1,000 rabbits are just enough to support a constant wolf population of 80. There are neither too many wolves, which would result in fewer rabbits, nor too few wolves, which would result in more rabbits. Now in part B, it says, use the system of differential equations to find an expression for dw divided by dr. Well, dw divided by dt is going to equal dw divided by dr times dr divided by dt. So we want to be able to use the chain rule to eliminate t. So in this scenario, if we want to find dw divided by dr, it would equal dw divided by dt, which is that equation. And that's going to divided by dr divided by dt, which is this equation. So now we have our dw divided by dr. In part C, it says draw a direction field for resulting differential equation in the RW plane. Then use that direction field to sketch some solution curves. So if we can think of W as a function of R, then we would have the differential equation here. And that's what we got from our previous step. Now, if we draw the direction field for this differential equation in figure 1, and we use it to sketch several solution curves in figure 2, if we move along a solution curve, we observe how the relationship between R and W changes as time passes. Notice that curves appear to be close in the sense that if we travel along a curve, we always return to the same point. So notice also that at the point 1,000 and then 80, which is right in the middle, is inside all the solutions of the curves. And that point is called the equilibrium point because it corresponds to the equilibrium solution where R is equal to 1000 and W is equal to 80. So when we represent solutions of a system of differential equations, as you can see in figure 2, we refer to the RW plane as the phase plane, and we call the solution curves phase trajectories. So a phase trajectory is a path traced out by the solutions RW. And as time goes by, now a phase portrait consists of equilibrium points and typical phase trajectories, as you can see in this diagram. Now in part D, it says suppose that at some point in time there are 1,000 rabbits and 40 wolves. We want to be able to draw the corresponding solution curve and use it to describe the changes in both population levels. Now if we're starting with 1,000 rabbits and 40 wolves, it corresponds to drawing the solution curve through the point 1,040. So here is 1,000, and then there's our point 40. So that is our initial point. Now figure 3 here is going to show this phase trajectory with the direction field removed. Now starting at the point P0 at time 0 and letting t increase, do we move clockwise or counterclockwise around the phase trajectory? So if we put R equal to 1,000 and W equals 40 into the first differential equation, then we would get the following. We would get 0.08 times 1,000 minus 0.001 times 1,000 times 40, which is equal to 80 minus 40, which is equal to 0. I'm sorry, which is equal to 40, excuse me. Now, since dr divided by t is greater than 0, therefore, if it's greater than 0, then we conclude that r is increasing at p of 0. And so we move counterclockwise around the phase trajectory. So that means we're moving from this point now to this point, which is p of 1. Now, we see that p of 0, there aren't enough wolves to maintain a balance between the populations, so the rabbit population increases. That results in more wolves, and eventually there are so many wolves that the rabbits have a hard time avoiding them. So the number of rabbits begin to decline, so at P1, where the estimate that R reaches its maximum population of about 2,080, now this means that at some later time, the wolf population starts to fall. So at P of 2, where R is 1,000 and W now is approximately 140, but this benefits the rabbits. So their population later starts to increase, and so now we move back to P3, or not back to, but 2.3, P3, where W now is going to equal 80, and R is approximately 210. So as a consequence, the wolf population eventually starts to increase as well. And this happens when the populations return to their initial values of R is equal to 1,000 and W is equal to 40. And then the entire cycle begins again. Now, if we use part D to make sketches of R and W as functions of t, from description of part D of how the rabbit and wolf populations rise and fall, we can sketch the graphs of R of t and W of t, and suppose the points P1, P2, and P3 in figure 3 are reached at times T1, T2, and T3. Then we can sketch the graphs of R and W as in the figure. So here we have R. So this is our rabbits. It's going to go down and then back up, and then go down and then back up again. And likewise, you can see what's happening here. So for the wolves, there's your graph. And now if we want a better comparison, then we can, to make the graphs easier to compare, we draw the graphs on the same axis, but with different scales for R and W. So here, number of rabbits, it goes from 0 to 1,000 to 2,000 and then 3,000 on the left side here. On the right side, we're using a scale where it goes from 40 to 80 and 120, and that allows us to be able to compare that a little bit better. So notice that the rabbits reached their maximum populations about a quarter of a cycle before the wolves.